So hello everyone, let us start. I think my screen is visible as if anyone is not responding here. I think my screen is visible. As anyone to respond whether my screen is visible or not?
Yes, sir, visible, sir.
Is it visible?
Visible, sir.
So let us start the assignment. Sample for week 10. The first question of today is a pulse modulated signal can be generated by passing the message signal to a differentiator circuit. Followed by a FM modulator. Option A is true and option B is false. So anyone to comment here? At least just try to say whether my voice is audible or not and my screen is visible.
Audible, sir, audible.
Yeah, thank you. So basically this is true. The reason is we generate this pulse modulated signal, like from the classes we know a pulse modulated signal can be generated by a FM modulator and differentiator circuit. The option is A. This was pretty straightforward question. Let us move to the question number 2. This is also a true-false pattern question. The question is, amplitude changes constantly in a frequency modulated signal. First option is true, option is false. So basically this question you can think also like whether this particular amplitude changes constantly for a frequency modulated signal. So whether amplitude changes in the frequency modulated signal, that is. So we know whatever the message frequency is, this gets modulated in terms of frequency. But amplitude remains constant. So amplitude does not change constantly for a frequency modulated signal. So the right option is false. Okay. Now let us go to the third question. The third question is narrowband FM signal is passed through a band limiter followed by a bandpass filter. So why we should do that for FM signal? So I am giving 4 options. The first option is to avoid amplitude variation. once more. A narrowband FM signal is passed through a band limiter followed by a band pass filter, and this is to avoid the amplitude variation of FM signal, or to convert narrowband FM to wideband FM, or avoid phase variation of the narrowband FM. So basically, this band limiter is used to avoid the amplitude variation of the FM signal. If we use this band limiter, what happens? There are some unwanted frequencies and the contribution of these unwanted frequencies just get avoided. So that's the reason this amplitude variation of the FM signal that may be reduced by using a band limiter after it passed through a high pass filter, a band pass filter. So all the unwanted frequencies will not come in this range if we use a band limiter. Let us go to the next question. So next question is, how a frequency modulated signal can be demodulated? How? I'm giving you 4 options. The first option is multiplying with a carrier frequency, and then passing through a low pass filter. Option B, passing through a differentiator followed by a envelope detection. Option C is passing through integrator. Plus then using the envelope detection. So which of the following is true? So again, this can be easily addressed from the lectures that FM signal can be demodulated by passing it through a differentiator circuit followed by a envelope detection. So these are from the lectures, I think. These are the easy questions. So let us go to the next question. Just let me check any doubt is there. Now in this question I will do a block diagram of a Armstrong FM transmitter and there will be a question about it. So I'm just writing the parameters first. F1 is equal to 400 kilohertz. FLO is equal to 21.6 megahertz. Del F1 is equal to 50 hertz. N1 64, N2 28. So these parameters will be required to solve this question. Now I am just drawing the block diagram. So MT is the message signal. It is going to a narrowband FM signal modulator. After that, it's a mixer kind of thing of F1 that is in the Armstrong FM, and then there is a frequency multiplier. And it is by n1 times. Then there is another modulator. This is the frequency that is coming, like FLO. Then there is another frequency multiplier, but this time with N2. The output is x of t. So what is the center frequency of xt? Here it is f1. So all the values are given here. Sorry. What is the frequency of the output of this local oscillator multiplying by after multiplying? So I'm not solving this question, but I am saying what will be the answer. So basically this frequency multiplier is getting multiplied n1 times, is multiplying this f1 signal. So here will be the signal is n1 f1, and then a local oscillator is coming here, right? So the output will be, the first one will be first center frequency is n1 time f1 plus this FLO, and if you calculate that, I believe this frequency is going to come like this. Just check with your calculator once. And the another one, F2C, will be N1 F1 minus FLO, and that should come around 4 megahertz. So N1 and F1 values are given in the question. This is the N1 value, and F1 value is this, and FLO value is this. if you substitute that, I think this is going to come like this. Is it clear? So the answer is like 57.28 megahertz and 4 megahertz. I think you should check at least once with your calculator whether these answers are coming or not. So only 3 information will be required, because this is a frequency multiplier that is multiplying this F1 signal, and then it is getting multiplied with the local oscillator. So what will be the output of this local oscillator? The output of the local oscillator will be, one signal is N1 F1 plus FLO and N1 F1 minus FLO. That two thing we have calculated only here. Okay. Now let us go to the question number 6. So for the previous question, what will be the output xt frequency? So to remember, we had this local oscillator multiplication there. There was a local oscillator, some blocks are coming, and there was a local oscillator, and this was the FLO, and then it was going through a N2 times multiplier, but the N2 value was given equal to 48. So what will be the output of xt? That is the question. What is the frequency of this xt signal, where xt is this signal? And to remember the answer of the last question, the frequencies were 57.28 megahertz and 4 megahertz. These two are the output here. So this question, the answer of this question will be pretty simple. You just have to multiply these two frequency by a multiplication factor of 48, because these are the frequency multiplier. So if you have noted the previous question, you can see that there is a frequency multiplier, but N2 was the value given as 48. So you just multiply these two, and the output you will get, this will be 4 into 48, 192 megahertz, and if you multiply this by 48, this will be 2745.6 megahertz. These are the answers. 192 megahertz and 2745.6 megahertz. Okay, I'm just drawing that question once again for the next question now. 7. Just drawing the block diagram once again. That is, it was like MT that is going to a in BFM, and here it is F1. Then next it is going to a frequency multiplier, that is N1. Then here is a local oscillator, hello. So the previous question was, then we are again multiplying with another frequency multiplier, of N2. The previous question was what was the xt. So till now what information we have got by solving the previous two questions, the F1 was given as 400 kilohertz. Then there is a frequency multiplier of N1. N1 was 64, and the first question was about what should be the frequency here. Let us say that is F2. We say that FLO 2 here. So 1 and 2, FLO, there will be two frequency components. We have find out of center frequency, that is FLO of 1 is 57.2 megahertz and FLO second frequency, that is 4 megahertz. Then here xt, and we say that if output C, there will be two defined frequencies, if output of 2, and these two will be nothing but just multiplying these two by a factor of 4. So the first one this one becomes the N2 was 48, so just a multiplication by 48 of these two factors. So the first one becomes 192 megahertz and the second one becomes 2745. So this is the summary of this block diagram. Now the seventh question I am just asking is, what is the maximum frequency deviation? In this FM transmitter? another output was given like the variation of delta f1, this can be here, it was noted in the first question. If you had noted this one, the delta f of 1 is 50 Hz. So that can be the variation of the f1 frequency. So the maximum frequency deviation is what? How much the delta f1 here can vary at the output. So the variation before these two frequency multiplier here was del f1 was 50 Hz, right? So after it goes through the first frequency multiplier, it becomes n1 del f1, the variation here. Similarly, here will be at the output this will be n1 del f1 and n2. It is for the first multiplier, this is for the second multiplier. So this is actually 64 and 48 into 50. It comes on about 153.6 kilohertz. So this is the frequency variation at the output, and this is the frequency variation in the input, you can think of, before applying the multipliers and after applying the multipliers. Okay, let us go to the next question. So that SSB single, that is the single sideband modulation type of thing, SSB modulation, can be viewed as a hybrid form of amplitude and frequency modulation. So why? Because this ST can be thought of MT cos 2 pi FCT plus minus that a Hilbert transform of MT into sine of 2 pi FCT. Now you have to answer the envelope of an SSB so just consider, so MT is the message signal where so basically the question is what will be this envelope. So you have to just comment on what is the envelope of this signal. So this is the SSP modulated signal. So I'm just writing the options. First option is m of t plus m of t. So B is m of t minus Hilbert transform of m of t. And option C is root under m squared t plus m hat squared t. So again, I have said that SSP modulation signal can be viewed as a hybrid form of amplitude and frequency modulation. Why? So see, here mt is the signal, that is sine cos 2 pi fct and sine 2 pi fct, and this can be written in this form. And this SSP can be thought of like this mt, the message signal, is just modulated by cos 2 pi fct. So the question is, what is the envelope of this signal is st? So you can simply solve it. The signal S of t is mt cos 2 pi fct plus m hat of t sine 2 pi fct, and there is a plus minus factor. So if we thought of some envelope detector, what happens? These two terms are orthogonal term. So basically the factor that will come is m square of t plus m hat square of t. That is the envelope. If you take this signal, you want to calculate what is the envelope of this signal, then the envelope will come like I phase into the quadrature phase, its amplitude only. Okay. Now the next question is, for the same question, I'm just writing the next question. What is the instantaneous frequency of the lower sideband? So for the lower sideband, what will be the theta c of t? So that is 2 pi fct that is for the carrier for this signal, 2 pi fct will come, and that is the tan inverse term comes here. So tan inverse of the amplitude, tan inverse of the real part, sorry, the imaginary part, that is the q phase part, q phase, by the in phase term, this is the I phase. So how we can got it, like we just, this is like differentiating with respect to just write in the short form ddt over mt. So this is thing that is happening. So from that we can calculate that now we do differentiating over that, over this theta ct with respect to t, and the factor that will come is fc of t is equal to fc plus the two terms. So let me write it. Fc of t, that is we get by differentiating over this theta ct, will be the constant fc plus, if we do the differentiation over this term, it will be m hat of t m dash t minus mt into hat of t, the first order differentiation, by 2 pi m square t plus m hat square t. So this will be the instantaneous frequency depending on the factor t. So at particular, for a particular t at t1, all the t's will be replaced by t1. So this will be the instantaneous frequency equation. So what we did, we first generated what is the phase, that is 2 pi fct plus some phase for the I term and q term. We can write the phase of this signal in this way. Then we just representing this particular phase with respect to time to get the frequency here, right? So we got the frequency like this as a function of t. So let us go to the last question for today. So question is, consider a wideband phase modulated signal produced by a sinusoidal modulating wave AM cos 2 pi ft using a modulator with phase sensitivity kp radian per volt. So if the maximum phase deviation of that PM signal is large compared to 1 radian approximate the bandwidth of the PM signal. So again, wideband phase modulated signal produced by a sinusoidal modulating wave, that is AM cos 2 pi ft, using a modulator with phase sensitivity is kp rad per volt. So one assumption is given that the maximum phase deviation of the PM signal is large compared to 1 radian. So we have to approximate the bandwidth of the PM signal. Now I am going to give you the options. Option A is FM kp AM. Option B is 2 FM kp AM. Option C is 4 FM kp AM. So just the question once again. Okay, let me solve the question. So what is the phase is 2 pi fct plus kp am cos 2 pi fc fm fmt. So frequency can be written as this 1 by 2 pi d theta I dt, that is equal to here fc minus kp am fm sin 2 pi fm t. So now we just use Carson's law. So if we use Carson's bandwidth rule, then we can approximate bandwidth equal to 2 into fm plus kp am fm, that is equal to 2 fm into 1 plus kp am. Now what was given in the question, that the maximum phase deviation of the PM signal is as large as compared to 1 radian. So from there we can write kp am greater than 1. Hence b equal to 2 fm kp am. Due to this condition is large compared to 1 radian, so that's why we are writing this condition kpm, and the bandwidth will be this. So the right option is B. Okay, so this was all for today's session. We'll meet in the next Sunday.